Hello, students. Welcome. This video is based on the Unit 4 test review. I apologize. I'm not going to be in class on December 11th. I have a mock trial field trip. So this will affect my day 2 class. So I decided to make this video. It should help the day 1 and day 2 class stay on the same timeline, and both classes will be able to watch it and refer to it if they need any guidance on any of the questions. So let's get started. The first 8 questions, we have to find the derivative. We also, with each derivative, we can use a chain rule, or we will have to use a chain rule. In number 1, we have both the product rule and the chain rule occurring. Here we have the product of two functions, and here we have chain rule 2x. I apologize in advance if I made any errors throughout this. I'm sure I'll find some as I'm going over the work. But I will make edits as we go if that's the case. I pre-did all the work out because I wasn't sure which day our field trip was going to be. But if you can just follow along, so we have the first function x squared times the derivative of the second. So the derivative of cosecant is negative cosecant cotangent. You'll notice that the 2x stays because that's our angle measure. So in both cases, the 2x reappears, and the derivative of the inner function 2x inside there is the derivative is 2. So I attach that on the end, plus the second function, which is cosecant of 2x, times the derivative of the first, which is 2x. The derivative of x squared is 2x. So that would be fine as an answer. I also simplified it. I moved a couple things to the front. I moved this negative, I'll use orange here. I brought the negative, the x squared, and the 2 right here. All that multiplication I brought to the front. So that's negative 2x squared. Leaving cosecant cotangent with 2x as the angle measure right there. And then I just moved 2x to the front. So either one would have been correct. Okay, number 2, we have a function inside a function inside a function. So we have a lot of chain happening here. We have something to the negative 1, right? That's our first function. And then inside that, we have the function itself. And we have inside that 6x. So it's like it's a double chain. So the first thing we do is we drop the negative 1 down as the exponent, and we bring it to the negative 2 power. You'll notice that this stays exactly the same. Now we derive the inner function, so tangent becomes secant squared. So we have that one. The angle again stays the same. Then we finally get to the innermost, that's 6x, and we derive that, and we get 6. So again, we derive the exponent. The negative 1 drops down, negative 2. The inner function stays exactly the same. We then derive the inner function, and the innermost, the 6x, still stays the same. And then we derive the 6x, and we get 6. If we rearrange, we want to attach the negative 1 and the 6 together through multiplication. We bring secant squared of 6x to the front as well, and then we have tangent of 6x to the negative 2. We could even write that in the denominator if we wanted to. Just the tangent of 6x squared would go in the denominator if we chose to do that. Okay, either answer is correct, or anything, again, I have a little note here, all equivalent solutions are acceptable for answers. Number 3, we have an outer function, u cubed, all of this cubed. So we're going to drop that 3 down and make it a 2. Then we have an inner function, and then we have an innermost function. So we have a lot going on again. So drop the 3, leave everything the same, bring it to the second power. Then derive the inside. The derivative of 1 is 0, and the derivative of sine is cosine. So we rewrite it as just cosine of 3x. Just that. That is the derivative of the inside. And then the derivative of my angle is going to be 3. So we attach that all together. Simplified, I move the 3's together with the cosine out front. And everything else stays the same. All right, number 4, we have an inner function here. We have cosine of negative x. We have an innermost, right? Whenever we derived x, when it was cosine of x, we attached a 1 on indirectly. We didn't even look at it. We didn't even write it. The derivative of x was 1. So all my prior questions I gave you had the derivative of x being 1. In this case, it's negative 1. That negative is going to matter. So we rewrite it in terms of, we write it with an exponent. So we switch from radical form to exponential. We drop the 1/2 down, and we bring the exponent to the negative 1/2. The innermost thing stays the same, the innermost function. Now we derive that innermost function. The derivative of cosine is negative sine. Again, the angle, repeated, stays the same. And now the derivative of that angle is negative 1. So we are deriving the inner and then the innermost function. Simplifying it, did I make an error? Nope. We have 1 negative. We have 2 negatives. So that becomes positive. The 1 times 1/2, right? So we have negative 1 times negative times 1/2. That's still just 1/2. Sine of negative x comes out front, and then we have cosine of negative x to the negative 1/2. So that is all correct. Simplified form. Okay, number 5. This is the product rule because we have the product of 2 items, but we also have chain rule because that entire quantity is being brought to the second power. So when we derive this second one, we're going to have to use the chain rule. So let's get going. We have the first function times the derivative of the second. So the derivative of this is you drop your 2 down, you bring it to the first power. Then we leave the inside exactly the same. And then we derive that inside. So the derivative of 2x squared minus 1 is 4x minus 0, or just 4x. All multiplications still. And then we rewrite, and then we do the second function times the derivative of the first function. So the only thing that changes is x cubed becomes 3x squared. This is addition. The product rule involves addition, right? First times the derivative of the second plus the second times the derivative of the first. I simplified it by pulling out a couple things that I saw, like 4x times x cubed times 2. So 4 times 2 is 8. X times x cubed is x to the 4th. So that's my 8x to the 4th. I could have distributed it amongst the other set here, but I chose not to. And then I just moved 3x squared to the front. Okay, I mean, we could simplify it more. We could distribute all this out and go a little bit further if we wanted to, but we'll just leave it like that. All right, number 6. 6 has the product multiplication along with we have some chain that's going to happen here. So the first function is x cubed. The derivative of the second derivative of secant is secant tan. Angle stays exactly the same. We fix it by attaching on the derivative of the angle, or the innermost function. The derivative of 0.5x is 0.5. And then we finish up with the second plus the second times the derivative of the first function. So the second stays the same, and that's the derivative of x cubed. Piece it all together and simplify. It looks like I moved the 0.5 and the x cubed stayed out front. Secant tan, and just move the 3x squared out front, and that's your simplified form. Could factor out a secant of 0.5x if we wanted to, but that's simplified enough. All right, two more. Quotient rule, yes. Instead of going crazy with the quotient rule and using the chain rule, we don't necessarily have to go crazy with it. X minus 1 squared is the same as x minus 1 times x minus 1. X squared minus 1 squared is the same thing as x squared minus 1 times x squared minus 1. And then when we factor x squared minus 1, we get x plus 1, x minus 1, x plus 1, x minus 1. So all I did was rewrite and rewrite again. I expanded it to get rid of the terms that I don't need. To put it in a simpler way, it's going to save me a lot of time and energy. You notice that rewritten, it looks like 1 over x plus 1 squared. I leave it in the squared form, and I'm gonna worry about using the chain rule when I use my quotient rule. So these, again, this function is equivalent to this. So, and let's see. So I start by the denominator times the derivative of the numerator, which is going to be 0, minus the numerator, which is 1, times the derivative of the denominator. So here's what we're doing. We're dropping the 2 down. We're leaving x plus 1 the same. We're bringing it to the first power. And then we're multiplying the derivative of the inside, which is 1. So it's really, we indirectly are using the chain rule even though we didn't need to write the number 1 there. All right. Oops, did I undo something I shouldn't have? Nope. Okay. All over, don't forget the denominator squared. So we have x plus 1 squared squared. So cleaning it up, getting rid of this will go, because that's 0. So we're left with negative 2 times x plus 1 over x plus 1 to the 4th. Now, if you notice, it's rewritten here, and we can simplify it further by taking out away one of these x plus 1s with one of these x plus 1s, making it 3 x plus 1s in the denominator. Again, all this is not needed. This would have been fine for your derivative right here. Or if you even went crazy with the chain rule, whatever you got as a result using the chain rule would have been fine as well. But again, it simplifies pretty nicely. So I left it in the simplified form. All right, we have the last one here. The only chain rule, this is product, I know that. You should see that as well. But because it's just an 8 and it's not a variable, it's applying the constant multiple rule, it's not going to matter, right? First times the derivative of the second plus the second times the derivative of the first, we see that the 0 yields nothing. So we're not going to do that. We're just going to leave 8 as a coefficient out front. We are just deriving tangent. The derivative of tan is secant squared, so the angle stays the same. Now we just derive the inside. The inside is x over 2, or it's 1/2 x, if you want to look at it this way. So the derivative of x is 1, so we just have 1/2. And we see that right here. So I attached on the chain link of 1/2. All right, 1/2 of 8 is 4, so I just simplified it to be a 4 there. All right, numbers 9 and 10. We're going to find the derivative and then evaluate at the location that we are given. So, wow, there's a lot going on here. I chose to use the chain rule, even though I could have just distributed everything together and got a huge number and worked with it. But just follow along with my work. I did the first function. Oh, let me change the color. I did the first function times the derivative of the second. So that involves us getting x cubed times, drop the 2, make it a 1, times the derivative of that inside, which is 3. Plus the second function times the derivative of the first. There's no chain rule there. Well, no implied chain rule. Okay. In theory, you're chaining x cubed, x, the derivative of x is 1. I don't need to put that chain link on though. I didn't have to, but I simplified it first. I moved a couple things around and connected them together, but you can immediately evaluate the 1 if you want to. So here you'll see that the 3, the 2, and the x cubed became 6x cubed. 3x minus 4 stays, and then I just move 3x squared to the front. Again, you do not need to do any of that. But we do have to evaluate it at 1. So I'm going to evaluate the derivative at 1. And you can follow my algebra, but we get -3 as a result. That means the slope at that location 1 is -3. And I think I just rewrote them at the bottom. Yep. Okay, the second one, we have a sine function. So we're going to drop the 2 down. Okay, so let me be a little bit more clear. We have a function on the inside, and we have an innermost function as well. So we're going to attach 2 chain links on. So the first thing I do is I drop the 2, and I make it a 1. Right, so really I should have written it like that. Let me clean up. Then I derive the inside. Sine of sine is cosine. Angle stays the same again. And then I derive the angle, which is 3. So when it's all cleaned up, we have 3 times 2 is 6. 6 sine of 3x cosine 3x. Putting in pi over 3 leaves it, pi over 6 is really nice because it becomes 3 pi over 6. So evaluating at pi over 6, we get 3 pi over 6, which is pi over 2. 3 pi over 6, pi over 2. So pi over 2, sine of pi over 2 is 1. Cosine of pi over 2 is 0. You should know these values by now, the 5 critical points. But if not, you can always type them in your calculator. But again, knowing them is really important. So 6 times 1 times 0 is 0. So the derivative at the location pi over 6 is going to be 0. All right. I can check all this work too. I can look at pi over 6 if I were to graph that. And it will result, you'll see a slope of 0 at that location. Okay, the next one. This one involves the chain rule as well, except we're going to be looking at them as whole functions. So instead of saying the derivative of x squared is 2x, or saying the derivative of x to the 5th is 5x to the 4th, we're going to look at it as the derivative of y is y prime, because it's with respect to x. So in this case, the derivative of my function f with respect to x is f prime of x. The same thing for g prime of x. So everything is listed in my table. It's really nice. I don't have much algebra to do. These are the values of inputs and outputs. So wait, I'm sorry. For this input, for this input, I have an output of 0 in that function. For this input, I have the output of -1 in that function. For this input, I have a slope of 3 of my first function. And for this input, I have a slope of 1 for my second function. The same goes for the last 4. Okay, so here we have g of f of x. So deriving the outer function gives me g prime. Remember, everything on the inside stays the same. Then I derive the inside. So what's the derivative of f of x? It's f prime of x. That's my chain link. If I want to go further, I could derive the x, but that's only going to be 1. But really, that x is an input, and so we're really ignoring that x. We're looking at g as a function and f as a function. So deriving it, we get those three things. We get g prime with the inside staying the same. Then we derive f, and we attach that f prime onto the end. So evaluating 0 in wherever we see x, we first put in 0 here and 0 here. F of 0, we get it from the chart. F of 0 is -1. So you notice I substitute in a -1 for that value. Now I'm looking at f prime of 0. So f prime of 0 is -2. Let me reset. F prime of 0 is -2. So I am going to use -2 for that value. You see it happen right there. And then the last value that goes here, well, so I'm doing this, I did the innermost function first. Then I rewrote it as g prime of -1 times f prime of 0. And for each one of those now, I write a new line. So g prime of -1, so g prime of -1 is 1. So I put in 1 there, I put in -2, so the final result is -2. All right, that's my final result. I wrote it down there. This next one is crazy. It's a product rule, the chain rule for the first function and the chain rule for the second. There's a lot going on, but let's take it one step at a time. The first thing we're going to do is look at the product rule. It's going to be first times the derivative of the second plus the second times the derivative of the first. Except each involves chain, so there's a lot attached. So the first function you see written here, the derivative of the second, drop your 2, g of x to the first power. Now you derive inside and you get g prime of x. Plus the second function, which you see here, times the derivative of the first, which is drop your 3, leave it as is, bring it to a 2, times the derivative of the inside, f prime. Now, I went through and I substituted in -1 for every location of x. And you'll notice that nothing changes other than the -1. I drop a few parentheses here and there that are not needed. Let me just put in multiplication symbol there. Yep, multiplication. Multiplication. Okay, so everything's multiplied, so I guess I don't really need to show you that. All right, so now I evaluate each one. So f of -1, zoom out, f of -1, f of -1 is 0. So it's going to be 0 cubed. Oops. Why am I using the same color? I don't know. So f of -1 is 0, so it's 0 cubed. Times 2, g of -1. So g of -1 is -1 times -1. And then g prime of -1, so g prime of -1 is 1. 0 times anything is 0, so that was easy. Now the second one, let me clean up. The second one is going to be g of negative 1 squared. So g of negative 1 squared, g of negative 1 is negative 1 squared, and then times 3, f of negative 1 squared. F of negative 1 squared is 0 squared, or 0, and it doesn't matter if there's a square there or not, because 0 times anything is 0. So the last one, f prime of negative 1 is negative 3, is positive 3. So really, there should be a square there. I'm going to put the square there anyway, just so it's consistent. Let's see. But again, there we go. That's the issue. Again, that result is going to be 0. So this whole thing turns into 0. Okay. Let's see. I'm just looking over my work. Yep. Because we're using the chain rule, f of x, or f of negative 1 shows up in both the first and second set of expressions. Okay, let's keep going. We're almost done. Particle moves along a line, so that its position at any time t greater than or equal to 0 is given by the function s of t equals t squared minus 8t plus 15, where s is measured in meters and t is measured in seconds. That's the most important part, is our units of measure. Find the velocity and acceleration functions, then answer the following questions. Show all work for credit. First thing I do is find the derivative, which is 2t minus 8. 2t minus 8. And then I derive that again, and I get 2. So, really nice. We have a constant acceleration of 2, regardless of if the function is slowing down or speeding up at a given time. It is a positive acceleration. Find the displacement of the particle during the first 2 seconds. Well, the displacement is based on the original function. That's its location at time t, or its position. So we are going to do the interval from 0 to 2, which is going to be s of 2 minus s of 0. It's going to be the end result minus the beginning. So we are looking at 0, 2. So we do s of t minus s of 0. I evaluate all of that. Looks like I get negative 12 meters. 2 squared is 4, minus 8 times 2. I just want to make sure that's the right function. Yep, plus 15, minus 0 squared, minus 8 times 0 plus 15. So we get 4 minus 16 plus 15. So that's 3 minus 15, negative 12. Yep. This means that the particle is located 12 units to the left of its starting position in the first 2 seconds. That doesn't mean it moved 12 to the left. It means it is 12 to the left. So it could have moved 15 to the left and then like 3 back to the right, or it could have moved 20 to the left and 8 back to the right, but where it ending up is 12 meters to the left. Find the average velocity of the particle during the first 4 seconds. Well, this is our displacement over our time. So again, the interval we're looking at is between 0 and 4. So it's going to be s of 4 minus s of 0 all over 4 minus 0. So it's y2 minus y1 over x2 minus x1. So looks like I get a result of negative 16 over 4, and I get negative 4 meters per second after all that work is completed. So it means it could have moved maybe 6, then 4, 8, then let's say 8 in the first second, and then 6, and then 2, and then negative 2. Whatever it ended up moving, it was an average of negative 4 meters per second. Okay, the velocity. When is the find the instantaneous velocity of the particle when t equals 4. Well, just find the derivative, evaluate it at 4, which we already did. We found this is our instantaneous velocity. Derive it, that's the derivative. So we evaluate it at 4. We get a result of 0. The instantaneous velocity at 4 seconds is 0 meters per second. This means the particle is changing direction at that time. We accidentally found where it changes direction. If we set this equal to 0, we would get 4. So that's where we see the change of direction. Again, this is the only answer I'm looking for. You don't really have to explain it. I chose to explain. Find the acceleration of the particle when t is 4. So we derive it twice, we get 2. There is nowhere we can substitute in. So if you look at this, if we write a of 4, we still get a result of 2. There are no t's left over. So the acceleration is always 2 meters per second squared. The rate of change is changing at 2 meters per second for every second. So 2 meters per second, or per second squared. Okay. At what values of t does the particle change direction? Well, we already found this earlier. Derive, set equal to 0. And we get 4. So the particle changes direction at 4 seconds. This is ironic that I was given something so easy. So it won't always be like that, but okay. When is the particle traveling in the left and right directions? The particle moves to the left when the velocity is negative, and it moves to the right when the velocity is positive. So a simple inequality could help me solve this. When it's negative is when the velocity will be less than 0. When it is positive, it's when the velocity will be greater than 0. So set up the same velocity function that we already used here. We know we're going to get the answer 4, but the question is, when is it lesser than 4? Well, think about it now. When is it lesser than 4? Well, when time is 1, 2, 3, right? It'll all be lesser than 0 when the time is before 4. But put it in an inequality and solve it, and you get that result. T is less than 4. That is when it is negative. When t is greater than 4, that's when the function is positive. So it is moving left between 0 and 4 seconds, and then right after 4 seconds. We can't go before 0 seconds, and we don't want to use less than or equal to. Personally, I don't know what's happening at time 0. It has initial velocity of some sort, so I don't, most likely at time 0 it was moving left, but again, at time 0 there was no movement, so this, just leave it without a lesser than or equal to, or in this case, if you look at t greater than or equal to. So 0 less than or equal to, just leave it without the equals. Okay, next one. Here's a rock. It gets launched at 160 feet per second, and that's where you see 160 t. For every second, you know, that has an influence. Minus 16t squared, well, when we derive that, we'll get negative 32. So we know that we're dealing with feet per second. So the derivative is 160 minus 32t feet per second. That makes sense because 160 was its initial velocity, and gravity pulls it down at the rate of 32 feet per second. For every second it's up there, it is slowing down. So, cool. The derivative of that is negative 32. My acceleration literally is gravity. It's feet per second per second. Okay, how high does a rock go? Well, the rock is going to go to its maximum height when the velocity is 0, because it's going to then fall back to the ground. So we have to first find the time, and then we can solve for the height. So find the velocity, set it equal to 0, which you see here, solve, and you get time is 5. After that, we evaluate 5 in the height function, the original function. So we have time, we substitute time in, we get 800 minus 400, we get 400 feet. This rock reached a maximum of 400 feet at 5 seconds. So when does a rock hit the ground? Well, it's when the height function is equivalent to 0. So we take the original height function that we were given, we set it equal to 0, we factor. Here's what you don't want to do. You don't want to divide by t. If you divide both sides by t, you get rid of a t on the left-hand side. You still have a t on the right-hand side. Yes, vice versa on the left-hand side. Yes, you cannot divide by 0. So t isn't supposed to go away, even though 0 over t is 0. So instead of doing that, you have to factor the t out and solve both the t and the 160 minus 16t for 0. Here you see t equals 0 when time is 0. Here you see time being 10. We have 2 times when the rock is at a height of 0. But when does it hit the ground? Well, the rock launched at 0 seconds. So when it lands on the ground, it's 10 seconds. So I simply said 10. If you put the answer 0 and 10, I won't mark you wrong, but just understand that 0 is not the time it's hitting the ground. That's the time it left the ground. All right. At what time is a rock 256 feet in the air? So this one does have 2 solutions. It's not on the way up or on the way down. It's both on the way up and on the way down. So when does h equal 256? So I set that equal to 256. And then to factor, I'm going to need to move the 160t over to the other side and the 16t to this side as well. I moved it to the left because I looked initially at t squared and I said, wait a minute, I don't want it to be negative, I want it to be positive. So that said, you know what, easiest way is to move everything left. So moving everything to the left gives me positive 16t squared minus 160t plus 256, that stayed positive. Factoring, in this case, I divided by 16 first, made it easier to see what my factors would be. Again, that's just to make it easier. You don't have to. You would get something probably a little bit more obnoxious. You'd probably get 4t minus 32 times 4t minus 8 or something similar to get those. Just divide by 16 if you can. You get this as a result. Factor and solve for when those are zeros at 2 and 8. Because this is a nice, perfect problem where a rock is not influenced by anything like friction or any other variables, you get a nice 2 and 8. 2 seconds after it launched, 2 seconds before it hits the ground. What is the average velocity of the rock in its first 4 seconds of flight? We are looking between the interval of 0 to 4. So it's going to be the average, which is going to be s of 4 minus s of 0 all over 4 minus 0. Evaluation will give me 96. So the average velocity is 96 feet per second. Just be careful with your algebra. It started at being launched at 160. Every time we applied negative 32 to it, it was slowing it down. So in the first 2 seconds, it went from 160 to 128, down to 96, down to 30, 30, whatever. Yeah, and the average of that is 96. Okay, the next one, what is the instantaneous velocity at 3 seconds? Well, oh, let me clean that up. I'll leave it highlighted for your notes. Okay, instantaneous velocity is the derivative. Whoops. Okay, so evaluate the derivative at 3 and you get 64. So 64 at 3 seconds. And that is feet per second. The speed of the rock at 6 seconds. So the speed is the same thing as the absolute value of velocity. So it's the absolute value of the derivative. We know the derivative is 160 minus 32t. So we are going to evaluate that. We get 160 minus 192. We get negative 32. Do not make that a positive. Absolute value is an operation that occurs after every single thing inside has been combined. You do not make it 160 plus 192. That is crazy velocity, which would make a crazy speed. You have to do the difference of them first, get a negative difference, and then apply the final operation positive to make it positive 32. And speed is not feet per second squared. So we're going to cross that out. I'm going to update that on my master copy. It must have been a copy paste error. Let me just make sure all the units are okay for other ones. Yep, because only acceleration, feet, seconds, second, feet per second, okay? Only acceleration is feet per second squared or meters per second squared. Okay, so that's that. Just cross it on your papers. They were probably already printed. And I'll update them for next year. I think that's it. So here's where, yep, I'm going to end the video. And I hope this helps for the day I'm not in class or for any other time you would like to watch it. All right, take care.